firstly, I'd like to thank the organizers for the invitation. So I have been studying the moduli of singular curves on K3 surfaces. So the origins of this topic are very classical. To fix the notation, I will let BH be the stack of primitively polarized K3 surfaces where H squared, L squared equals 2H minus 2. And then the Severi variety, which I will use slightly non-standard notation. So I let VGHK XL be the Severi variety which parametrizes, divises D in KL such that D is integral, nodal, and has geometric genus G. So I think all my indices are quite non-standard, and I apologize for that. Now, this is a very classical object. It's been studied obviously originally by Severi, particularly in the case of a plane. And the case of K3 surface has been much studied because the degree of the closure of this has a lot of importance in string theory and so on. And there's all these formulas by Brill, Yale, Zaslow, Brian Leon, Katz, Clem, Buffer, and all those kind of things. So this comes with a moduli map. VGHK XL to MG, where MG is the linear Mumford stack of curves of genus G, which simply takes a point D to the normalization D twiddle. But unfortunately, if you just set it up like this, it's not quite properly defined because you can't really, if you compactify this to the closure, this doesn't extend to a map onto the compactification here. So we need to come up with another compactification rather than taking the usual compactification in the linear space L. So what we do now is we introduce stable maps. Okay, so this is a parametric approach. So the nodal curves D are in one-to-one correspondence with birational maps F. So they're in one-to-one correspondence by rational morphisms such that the geometric genus now, so this is smooth. This is birational. And the genus of D is G. And the cycle F star D is KL. Okay, and then this space has a compactification. What did I call this? I call this WG So the space of these morphisms has a compactification WGHKXL. Oh, sorry, and with the condition that the image is nodal. Right. This has a compactification WGHK parametrizing stable maps F, I will call this B to X, where B is nodal, connected as arithmetic genus G, where of course we fix F star, F the push forward of B to be KL, and F is stable. So stable means for any component E of B isomorphic to P1, it meets the rest of the curve in at least 3 points. Okay, so let's say something about the deformation theory of segments. Oh, so I should say, and the point of doing this is now we have a map. There exists a moduli map. Now it's an arithmetic genus. Here it's the same. This is smooth. But in the compactification, you allow it to be nodal, and so then it's arithmetic genus. And now there's a moduli map. So I should have said arithmetic genus probably. Eta. So the point is, we can't compactify this to L, but we can now have a compactification. And then you see this map is a very stupid map. It's just forgetful map. L goes to mg bar, and you just take F to the stable model of B. So stable here means that if E is a component isomorphic to P1 and it is contracted to 1 point, then it must meet the rest of the curve in 3 points. But there can still be components which are not contracted to 1 point, but only meet the rest of the curve in 2 points, and the stable model means you contract these. So there's a difference between the stability for a map and stability for the curve. Okay, so I now need to talk about the deformation theory. So if we assume that the stable map F is unramified, so I should say that this deformation theory is due full generality to Li and Xian. If we assume that F is unramified, then there exists a bundle called the normal bundle of the morphism fitting into an exact sequence. Yeah, F is a map from C to X. Okay, so by definition, the normal bundle fits into this sequence. Now, if we take determinants, you see, because it's a K3 surface, that this is isomorphic to omega C, and the tangent space at F, the omega G HK XL is just given by H naught of NF. And the obstructions at F lie in, but are not the same as H1. And it's not an inclusion due to results, well, originally due to Rand, but in this context, maybe Cool-Thomas. Essentially an argument of Bogomolov-Hasseltschenko, because I'm not assuming that F is birational. So, okay, and this is just C, so there's no obstructions. So the dimension at F is just G. Okay, so now we want to relativize this. Oh, one other thing I wanted to say. So, I'm going to do this later. Okay, so now we relativize this. And then we have a relative stack VGHK over BH with fiber over XL given just by the severity variety. Likewise, we have stack WGHK given by the moduli space of stable maps. Okay, and I will let TGHK in WGHK denote the open substack of pairs. So I'll write an element in here as a pair F, B2X, and L. And then this open substack such that B is smooth and integral. F is unramified. And F is birational. So I'm not assuming that FB is nodal. So in particular we have, but if for a nodal curve, the normalization of a nodal curve is unramified. So this contains the universal severity variety. But it may contain many more points. So for example, if you have a triple point, an ordinary triple point, then analytically, locally, the normalization morphism has three components going to the three different branches, so this is also unramified. So this is a much weaker condition than merely having F being nodal. And deformation theory of this by this is very nice. It's smooth and every component dominates BH. And also, this is dense due to a direct application of a theorem of Zariski. Well, maybe Chen. Chen slightly adapts this theorem of Zariski to prove that this is dense. And I should say at this point, it's a conjecture due to many people, probably due to Ran, Chen, and Deju, who really explicitly stated it, but Chen stated it for rational curves, the case g equals 0, that BGHK, and hence TGHK is irreducible. And this, you can prove this for a small number of nodes, i.e. if G is very close to H, but in general it's widely open. Okay, so the question I want to consider is what is the dimension of the image of eta restricted to TGH. It's another interesting question to try to describe what the image is compared to the Brill-Noether loci. And I have some results on this, but today I'm just going to talk about the dimension of the image because there's not enough time. So this image, you can think of this as just parametrizing the space of genus G curves which have a nodal or more general not so, for VG, which is dense, you can think of this image as parametrizing those curves which have a nodal model on the K3 surface. So first I'd like to motivate this by studying the smooth case and by stating the known results in that case. Okay, so we're looking at this morphism, and the dimension of this, the moduli, the stack of primitively polarized K3s has dimension 19. So this has dimension 19 plus G. This has dimension 3G minus 3. And 19 plus G is less than or equal to 3G minus 3 for G at least 11. So a naive guess would be that eta is generically finite for G greater than or equal to 11. But this turns out this can't be true because the case G equals 12. So first I will study the smooth case. This is the case where G equals H. So the number of nodes is just 0. Yeah, I mean generically finite onto its image. There's different, people seem to have different definitions for generically finite, but this is the definition that Mukai uses the phrase generically finite to mean generically finite onto its image, so I just copied that. Okay. So in the smooth case, G equals H, and this is just a projective bundle over BH. And then this is obviously irreducible in this case, so you don't have to worry about that. And then the results are case K equals 1, due to Mori-Mukai in 83. And it says that the smooth case G equals H. In other words, number of nodes is nothing. K equals 1. So the primitive case, where the curves lie in the primitive class. Okay, then Mori and Mukai proved that eta is generically finite for genus equals 12. For genus not equals to 12, and it fails at genus at least 11. And it fails for genus equals 12. And for K at least 2, there's a result by Chiliberto, Lopez, and Miranda. And actually, I cited the wrong paper in my introduction to my paper in the archive, so I'll just give the full title here. I just made a bib tech error. So. Classification of varieties with canonical curve section. This was 1994. And they proved that if K is at least 2 and the genus is at least 7, then eta is generically finite. And I think these are optimal. So yeah, so actually if it's non-primitive, it's generically finite on a greater bound. So for example, if you just look at quartics, which is G equals 3, then if K equals 4, there's a pencil of quartics over every curve, so it fails, but then it holds again for K greater than or equal to 5, for example. Yeah. There's a single, yes, there's a single K3 surface with a polarization such that it lies in KL. As twice the polarization. Yes. They proved essentially that the differential is injective. They explicitly calculated the differential and proved it's injective. So they didn't actually state it, but they stated the cohomological conditions. In another paper, they more explicitly go into the details. In an earlier paper, they sort of go into why these cohomological conditions imply it more explicitly. But I think this is pretty well known. So they proved it by degeneration to a cone and then calculating using this degeneration what the dimensions are. So I just wanted to say that this is done by degenerations to a cone. So it's very different to this approach. In modern language, you would call this approach non-Abelian Brill-Noether loci of rank 2. This is a very different approach using degeneration to a cone. Okay, so my result says that, firstly in the case K equals 1, the primitive case, there exists a component I in TGHK such that eta from I to mg is generically finite. If G is at least 15. And I can improve this. So we just have finitely many cases left between 11 and 14, and in most cases I can improve this. So if we let, so this is now a condition. So I haven't used H yet, but I can improve this depending on the combinatorial properties of H. So let RH be an integer such that H minus 11 equals H minus 11 on 6. Then if RH is not equal to 5, then this implies eta is generically finite for G greater than or equal to 13, and if RH equals 0, then can improve to G at least 12. So my method of proof is very similar to Mori-Mukai's, which explains why I kind of have these combinatorial things popping up, because they break theirs down into many cases, depending on some combinatorics if you really read their proof. So it's very similar to them. And the case where K is at least 2, H is at least 8, then there exists a component I such that eta is generically finite for G at least, I think, 18. And we can likewise, you can improve this depending on some other combinatorial properties of H, which I'm not going to write down now. And both of these are proved in a similar way using a technique very similar to Mori and Mukai's. So in particular, this gives you a new proof of this result for all genus other than 7, which is, maybe I've got the G's and the H's mixed up here. No, because G equals H here. For all genuses other than 7, which doesn't use degenerations to cones, it just uses a kind of explicit approach of Mori-Mukai. So now I should talk about this approach. And also a nice property of my proof is it kind of gives, so it was, for some people it was a kind of a bit of a mystery what exactly goes wrong in the case of genus 12, and there's a very simple explanation for it in my case. It's just because otherwise some curve is no longer stable. Okay. So we start with the following proposition, which comes from, it doesn't really come directly from anywhere, but it's very similar to what is done by Mukai. Section 3 of duality of polarized K3s. So let S be a K3 surface. with rank 2 Picard groups, ZL, ZE, L squared equals 2H minus 2 for H at least 11 and H odd. And take E to be an elliptic vibration, so E is an elliptic curve which squares to 0. And we will set LE equal H plus 1 on 2, so that this spans out a G1 H plus 1 on 2, which is just one lower than the expected general. So this is not a completely general curve, but it's just slightly general with generality. Then he proves that if we let D, he doesn't actually prove it exactly in this paper, but if you combine the results he proves in this paper with results he proves in other papers, he ends up proving the following. Let D in L be a general smooth curve then eta in this case H equals G, so THHK to MH is in fact bijective onto its image near the curve D. So I'm writing as THH1. Okay? Okay, so if I just draw this, then we have an elliptic vibration. And D meets E, as the Mori-Mukai is, in H plus 1 on 2 points. And if I set B equal to OE on S, restricted to D, then this is a G1H plus 1 on 2 on D. Call this B because I want to call A its adjoint, which is omega D tensor D joule morphic to O L minus E. Okay, now consider the map induced by A into PK, where K equals H naught DA equals, you can check it's actually the same as H naught S L minus E. And because this is the same, this factorizes through the closed emergence D to S and then S to PK, and you can check that this is actually ample, just by phi L minus E. Okay, so we have this diagram here, which is really important. Yeah. Everything okay? Okay, so now notice that so here we need to use H as at least 11 to get that L minus E is very ample. So now note that L minus 2E squared equals minus 4. And in fact, it's easy to show that L minus 2E is not effective. So the way Mukai does it is he just proves that there are no minus 2 curves here. Okay, now let Q in PK be a quadric containing D. Since L minus 2E is not effective, we must have that Q contains S. Otherwise, the intersection of Q with S would be something in 2L minus 2E, and since it contains D, it would then have to contain an effective divisor L minus 2E, which is not effective. So Q actually contains S, which means that the quadric hull, which is defined to be the intersection, so the quadric hull of D is defined to be the intersection of all quadrics containing D. This then equals the quadric hull of S, which also equals S by St. Bernard's theorem. So in particular, we have reconstructed S from D together with A, or equivalently together with B, together with the G1H plus 1 on 2B. And moreover, we've actually reconstructed the embedding D into S because it's just the embedding of D into the quadric hull of D. So this implies the claim. So the only K3 containing D is S by this argument, and the only embedding of D into S is the embedding of D into the quadric hull of D. Okay. Oh, further, I forgot to say. You still don't know a priori that there's only one A, that this A is uniquely determined, but together with the G1 and 2B, but B is uniquely determined by Donaghy-Morrison. So Donaghy-Morrison have this very nice paper where they show if a G1 something which achieves the maximal Clifford index of the curve has to come from some divisor on the K3. And you can check in this case it implies that B is uniquely determined. And this is actually how Mukai proves his results on non-Abelian Brill-Noether loci in the case of G equals 11, because this quadric hull can actually be identified with a locus of rank 2 vector bundles on D satisfying some Brill-Noether properties, so they have a certain number of sections. They can actually be identified. So then this gives him his results on non-Abelian Brill-Noether loci. Okay. So Sketch's theorem. Okay, now we consider K3 surface S. So take a similar diagram to before. We have a D, we have an E, intersecting in H plus 1 on 2 points. And now I want to, so if you just have a general Picard rank 2 elliptic fibration like this, all singular fibers must be integral. And in fact, for a general one, all singular fibers will be rational with one node. We want to consider the case where we instead allow one of the singular fibers to be an I2 fiber. Like this. So gamma. So then we have a rational curve gamma, which does not intersect E, but intersects D. And we can choose how many points we intersect it in. So the Picard of S is ZL, where L is a class of D, plus ZE plus Z gamma, where I'm going to fix H equal to 11. And then L squared equals 20, because 2 by 11 minus 2. E squared is 0. Gamma squared is minus 2. And E gamma is 0. And L gamma is some number A, which varies between, I should have said, LE is 6, so L gamma has to be less than 6, so A goes from 1 to 5. Well, we can just pick the integer appropriately. Okay. Now you can check that this proposition still goes through on this K3 surface. So you just have to do some calculations on the Picard of this, which is slightly more complicated because the Picard rank is 3. But then everything goes through. And as in the previous case, eta T11, 11.1 and G is birational onto its image. Rational near D. Where D is just something in L. So for this, you just have to check that the conditions we needed here, such as Donaghy-Morrison and that L minus 2E being not effective, are still satisfied, and it's not hard to check. Okay, so now let lambda be the rank 2 lattice generated by elements. We'll call them L dash R with L dash squared equals 20, R squared equals minus 2, L R equals A. A equals some integer H. What should I call this? I should call this H plus 1. Then, okay. So for almost all cases of RH, there might be some conditions on RH you need, but essentially in all cases, we have a primitive embedding lambda into pick S. Just takes L dash to L, a primitive embedding, and R goes to ME plus gamma. So what we do is ME plus gamma is some class which goes to -2. It's not really a nice class, but it squares to -2. We deform L and ME plus gamma for whichever M we want to a K3 with Picard rank 2 generated by elements L dash and some class which squares to -2 and meets L prime in some number of points, which can now be a very high number of points because it's A for whatever A we want plus 6M. Okay? And now for the general such K3, we have that this property, because this is an open property, this property still holds for D and L prime. And you can now check that R will meet that this R will be a smooth rational curve which meets D prime and L prime transversely because this is very ample. And so we end up with a diagram. So we degenerate K3, I call this S prime, with Picard S prime isomorphic to lambda. We generate this to S, and then we have that for D prime in L prime general, eta is birational near D prime, and R is a smooth rational curve. Meeting D prime transversely. Does this seem okay? Okay, but now we are essentially done. So now we have a stable map. So shall I write this as D prime? Then we have to leave at least 3 nodes here on some P1, which gets mapped to D prime union R. So this is R, so we get this stable map by taking partial normalization at some nodes, but I want to leave at least 3 so that this curve is stable. By picking, so consider F by picking less than equal to number of points of intersection minus 3. And the claim is that eta is generically finite near F. proof. Suppose we have a one-dimensional family of maps. So I will call this B. And since B is stable, B is just equal to its stable model. So what we have to prove, the fiber of eta near F will be a one-dimensional family of maps with constant base B into K3's xt, such that G0 is F. So we have a one-dimensional family of maps B into xt with G0 equal to F. Okay, but if we let Jt be the closed immersion D prime, the family D prime into B into xt, then this is a closed immersion for T near 0, because it's a closed immersion at the origin, and being a closed immersion is an open property for a family of maps. So this is a closed immersion for T near 0. But we've just said that we can reconstruct xt from D prime. Okay, so this implies that xt is x0, which I call S prime, I think. Okay, so we have a family of stable maps on one curve, and now we just use that Gt is unramified for T near 0. This is again an open condition. And rational curves on a K3 are fixed. So because rational curves on a K3 are fixed, the other component is also a constant map. And you can only glue it infinitely many ways because the whole thing has to be unramified. So you're done. That's it. And this shows you explicitly what goes wrong in the case of genus equals 12, or H equals G in a smooth case. So to try to apply this technique, you will be trying to look at maps like this, genus equals 11, and some gamma, which meets it in 2 points, some rational curve R. But then this is not stable. So you have to take the stabilization, which is some nodal curve. And then you've lost completely your D prime. So you can't conclude that the family is constant. Because you've lost your D prime, it's not you no longer have this because this is not D prime. So you no longer can reconstruct your K3 basis. So this is my explanation for what the problem is in genus 12. Okay. I don't think it's not much time, but what can I say about the... Yes, actually, I haven't really used stable maps here much. You can actually do this without using the deformation theory of stable maps. Instead, you just use Tannenbaum's theory of choosing a certain number of nodes such that the curve doesn't get disconnected, and then you can do it like that. But you really need stable maps in the case where k is greater than or equal to 2. So we have so in this case it's just a similar idea. You construct unramified maps F, say D prime union T into S, where, so the map will be unramified. Actually, its image will be highly non-reduced. But again, such that you have the property that eta is bijective near D prime. And then you have to check, really, here it's just automatic that this lies in the closure of my open substack TG. Here it's a little bit a little bit harder to check there's a lies in it. But you find examples for which you can check it, and then you show it's bijective near eta, and this is unramified where T is rational. Then you apply the same technique, and the kind of things you do is for say, you take a rational curve M with M multiples of a nodal curve, then there exists a non-ramified morphism from M copies of P1 to this, where you just glue at the nodes in the opposite branch direction. So this is the kind of trick you use. Okay. No, because Brian Leung's degeneration has a section of P1. It just doesn't have a rational section. So this has a multi-section. D is a multi-section, but the thing which maps down to P1 is, yeah, it's a different kind. It's really a modification of the generation used by Mukai in this paper, duality of polarized K3s. This is where it comes from. Yeah. Oh, so you're asking for the other, you're asking for the surjectivity of this map eta. So in the case, oh, you're allowed to vary K as well. It's not clear. So one way to prove that you couldn't do this would be if you could give like some obstruction for a curve to have a nodal model on K3 surface. And they have kind of things like an obstruction, but the problem is they only work for a small number of nodes. And the obstruction they have, it gets weaker as you take more and more nodes. So as far as I know, it's definitely possible. Like, I think it might be even true, but I'm not going to claim that it's true. But I think it's highly plausible.